Okay, well, thank Robert. Well, thank all the other organizers for putting this together. This very interesting program. I'm sorry I couldn't come, although I really wish. Actually, I wrote my first paper on Schrodinger equation exactly at Schrodinger Institute. So it's really a fun memory of this great institute. Okay, so today I'm going to talk about some recent work, actually a new field that I entered in the last half of a year or so. It's about quantum algorithms for differential equations. And very recently, we also did some work that's related to uncertainty quantifications. So the joint work with my colleague, Nana Liu, who is, she's really expert on quantum computing. I'm new to this area, so I learned quite a bit from Nana. And she actually got her PhD from Oxford and was selected by the MIT Technical Review as a 10 innovators in Asian Pacific region under the age of 35. All right, so I'd like to play this. This is an uncertainty quantification workshop, so I would like to show you these slides.
How do you stay relaxed?
I play mahjong with my girlfriends once a week. That's probably my. That many people play mahjong in this audience? Because that would make me so super happy right now.
Wow.
I really.
How do you play mahjong? And you don't have to give me all the rules, but
I could not.
I grew up with a set of my grandmothers in the house.
Did?
Yeah, beautiful bamboo with like the ivory front, really old, like 100 years old. They look beautiful. I can't imagine how you play. It looks so complicated.
Can't make heads or tails of it.
No.
Yeah.
What's the point?
It is. Well, here's the point, and my team here, my people can back me up on this. It is that the concept of it is to create order out of chaos based on random drawing of tiles.
Wow.
That's deep.
That is deep.
Yeah.
Okay.
How do you stay relaxed?
So it looks like, well, actually, it's a famous actress summarize. That's the best summary about mahjong, which is very popular in China, and also very good summary about what uncertainty quantification is. Whenever I give a talk on UQ in China, people ask me what is UQ. So I said what she said in the best possible way.
How do you stay relaxed?
All right. So what this is the outline of my talk. First, well, quantum computing is probably not very familiar for many people. So I will give a very quick, short survival kit for mathematicians, what the quantum computing is. And then I will talk about our new work on quantum algorithm for nonlinear PDEs. Particularly, I will mainly concentrate on Hamming-Jacobi equation and nonlinear scalar hyperbolic equations. And then I will talk a little bit about the uncertainty quantification for PDEs in quantum computing. So why we need quantum computing in first place? Well, the reason, of course, the classical computer has reached a certain limit. For example, we all know this Moore's law, which says every 18 months, the speed of computer will double. But it certainly has reached to its limit because the size of chips is almost, it's nanometers, right? 2 nanometers for the latest chip. There's also other restrictions due to bandwidth and energy and memory and so on. So actually the concept of quantum computing was first brought by Richard Feynman in 1981, in which he was conjectured, he asked the following question: can a computer efficiently simulate quantum mechanics? Right? We know, the most difficult challenge for a computation is probably simulate. Well, this is the Schrodinger Institute, simulate unbodied Schrodinger equation. Usually for realistic applications, this n can be easily hundreds, right? So I have to solve a PDE of several hundred dimensions. And what the idea of quantum computer is well, let the computer itself to be built of quantum mechanical elements, all right? So he even conjectured how to make such a quantum computer. He suggested use an array of spin half particles, which is actually what is now called the quantum bits, qubits, this idea. So I give a very, very short review of, basic introductions of very fundamental, very basic things about quantum computing. If you know it, I apologize. You can skip the next 10 minutes. So basically, the classical computer is based on this binary electronic signals, right? 0 and 1. Then you pass through this classical computer. Your output is also, this binary electric signals. But a quantum computer actually compute quantum states, all right? So you start with a quantum state and it pass through certain operators, usually unitary operators called quantum gates. And then you end up with quantum states, all right? So these quantum states are not classical data. So if you start with classical data and you want output data, then you have to do the encoding. You have to make quantum state out of classical data. That's called encoding. And you have a decoding. That's usually called a measurement. All right, you have quantum states. You want to read out the data. That's called a measurement. And very often, this quantum from quantum state to quantum state usually is called quantum subroutine. And this input and output, that's usually very expensive. It's so expensive, and most of the time, you destroy all the quantum advantage that you gain during these quantum subroutines. Well, the quantum computer is made up so-called qubits. So it begins with the basic bits, which is basically 2 unit vectors, okay, in 2 dimension. It's 0. This is a direct bracket notation. So this 0 vector, 0 cat is basically the 0 and 1 cat are these basic unit vectors in 2D. And then you do a qubit is a linear combination of these 2 basis vectors with the coefficient A and B are both complex numbers, all right? And you have normalized such that this vector has norm 1 per side. And qubits is basically a tensor product of these qubits. If you have many qubits, all right, they do a tensor product of these 2 by 2 dimension 2 vectors. And usually we work on the Hilbert space of complex value and dimension n, Cn. And typically you choose capital M to be 2 to the power n, little m. All right, this little n is usually called the n qubits. And what do we expect from a quantum computer? We expect so-called quantum exponential speed up, because typically, if you design properly, a quantum algorithm will cost polynomial of little m, while the classical algorithm usually is polynomial of capital M. So there you save a logarithmic factor, right? You get this exponential speed up with the quantum computing. And well, the quantum computation is done through quantum gates, which are basically unitary matrices. For example, most of the important unit matrices are the Pauli matrix. So we have a direct of the Pauli institute here in the audience. So we start with the Pauli matrices and Hadamard gate. These are all 2 by 2 matrices. If you have to deal with 2 qubits, you have to use a 4 by 4 matrix. And the most popular one is so-called control NOT gate, C0. The way it works is that, if you get two qubits are basically a tensor product of 1 qubit, for example, in 2 qubit. Well, in 1 qubit, of course, you have these 2 vectors, unit vectors at the basis. In 2 qubits, you have these 4 unit vectors, which are basically tensor product of 2-dimensional qubit. So you have these 4 basis functions. And if you multiply this C0 gate matrices to one of this, what you get is that the first 2 unit vectors, you do nothing because the submatrix, first 2 by 2 submatrix is identity matrix, right? If you apply C0 gate to the first 2 bases, 0, 0, and 0, 1, and you do not change. And the next 2 vectors, you basically switch them, all right? So that's how the C0 gate works. And usually we draw pictures to describe so-called quantum circuits, all right? So here you start a quantum state per psi, you multiply by this unit vector u, you end up at the u per psi, all right? So for example, if 1 through this x gate, you get a 0 vector through x gate, you get 1. And 1 through the z gate is Pauli gate, and you get -1 and so on. And well, the C0 gate can be drawn like this. So if you have these 2 qubit A and B. If A is 0, actually do nothing. But if A is 1, you add to the vector B. But here the summation is more 2 summation, if so with 2 is equals 0. All right. And a very popular quantum algorithm is called a quantum phase estimate. That's through this various gate with Harmat gate and some other unitary operators. And as I said, a quantum computer start with quantum state and end the quantum state. And after that, if you want to get your classical data, you have to take this so-called measurement, of course, called quantum measurement. And the measurement usually give what the quantity of interest, for example, physical observables. And the measurement, what it does is to measure the probability of a certain outcome in the computational basis. All right, so it's a lot like a sampling game. And typically, because this sample is classical computation, the cost of measurement can be much higher than the cost of quantum subroutines. So if you want to design a very good quantum algorithm, not only you need a good quantum subroutine, you also have to do a very good job in this measurement, encoding and decoding. So what are the challenges for quantum computers? It's both hardware challenge and softwares. The challenge for hardware is that usually the qubits are there's a lot of noises. So if you do not have lots of qubits, for example, now the IBM or also China, these are the leaders of hardware in quantum computing. They can manage like between 100 and 200 qubits, but that cannot be used for realistic computation because there's lots of noise. So the computation results are highly unreliable, right? Also, loading classical data is very difficult because you have to load the classical data and make it to a quantum states. That usually costs a lot of computational resource. Well, there are also lots of challenges in software. For example, actually, in the classical computer, we have a debug, right? And if there's the code has trouble, you do debugging. And what I usually do is I just stop computation and I print out the data and I see where the data makes sense, right? But quantum computer cannot stop and do debugging because once you stop, you read out the data. That's a measurement. That's very expensive. Then you have to load this data back. You cannot do it. You cannot stop. You have to start from the beginning and at the output. All right. You cannot stop at the intermediate step. Also, the algorithm is very difficult because you have to work. All the algorithms have to fit into this quantum state. So therefore, a lot of operations in a classical computer, the quantum computer doesn't know how to do it. I always say this quantum computer is like an infant. You have to fit the infant with the formulas, right? You have to fit something that the infant can digest. Okay. Well, so far, the most successful area in quantum computing, one of the most successful is in algorithms for linear algebra problems, right? So there are a few successful examples. For example, this HHL algorithm. And so if you want to solve a linear algebra problem with a matrix M, so you want to solve Mx equals Y, all right? So this HHL algorithm this is the cost, all right? It's proportional to, so this M max is the max norm is basically the maximum entries in absolute value, all right? So that's M max divided by eta is the error accuracy requirement. The kappa is the condition number of M, and S the sparsity. So the sparsity is the number of non-zero entries in the rows and columns, all right? But then you have this log term which you can basically ignore. So it's quadratic in condition number and linear in sparsity divided by eta. Well, later this improved algorithm called CKS algorithm, where you can get rid of this case kappa square. It becomes linear in kappa, and also you don't divide by eta. All right. So of course, if the problem is well conditioned, you get a very good computational efficiency here. But once you know how to solve a linear algebra problem, then you can do a linear PDE. Because for linear PDEs, you can first discretize space and time variables, then it become a linear system, a linear algebraic system. Then you can use this linear algebra solver, quantum solvers, all right? But unfortunately, we know, if you discretize differential operators, usually the condition number is very bad. Typically, its condition number is order n, where n is the match point per dimension, or even n squared if you have an elliptic operator. However, despite this yield conditionalness, if you have a very high dimensional problem, you gain this quantum advantage. The reason is that capital N equals 2 to the power n, all right? And if you use little n qubits, and you gain the factor of logarithmic factor, right? So these quantum subroutines usually give you exponential speed up. However, this quantum subroutine only output the quantum state of x, not x itself. So if you want to get x, you have to do this quantum measurement. With Nana Liu and also Yu, who is a postdoc for us, and actually we sort of just summarize. We just analyzed the most popular finite difference algorithm for typical this most basic linear PDEs. And we implement those in a quantum linear algebra framework. And we want to see what is the quantum advantage, all right? And for example, for ODE, and actually, if you the classical solvers, for example, we compare with for the Ola and Kronecker-Nicholson, and the later is unconditionally stable, so that's called NT is the number of time steps. But the quantum algorithm actually does not see the difference between first and second order method, whether it's a conditional stable or unconditional stable. I don't see difference. And actually, even for ODE, you do not have quantum advantage. I mean, it's basically the same with the actual log factor. All right, so you do not save anything. I mean, the quantum ODE solver actually it does not help you. However, for heat equation, and here nx the match points in x dimension, d is the dimension of the space variable. So of course, there's some difference between explicit schemes and Kronecker-Nicholson, and you see this curse of dimensionality. You have nx to the power d. But if you do the quantum algorithm, you get rid of this power d. Okay, so you see that you do have an advantage. You do not have basically curse of dimensionality for quantum computing. And well, then for heat equation, actually you don't see any difference between the explicit method and Kronecker-Nicholson. But for hyperbolic problem, also you get rid of the curse of dimensionality. And again, I mean the classical finite difference method, for example, upwind scheme, has this n to the power d, while the quantum algorithm does not have n to the power d. Okay. We were also curious about, I mean, if you solve a multi-scale problem, for example, if your problem have a multi-scale, small scale epsilon, and for the classical algorithm, we know if you have a numerical method which does not, I mean, numerical parameters does not depend on epsilon, then those are the methods that you like. And here you see that if you do an explicit method for multi-scale problem, for a stiff problem, for example, stiff PDE, you have this cost which the cost will depends on 1 over epsilon, or epsilon small parameters. So you have to resolve small epsilon usually. If you have a nice multi-scale method, then you have a method that does not depend on epsilon, all right? At the quantum level, you also see that if you have a multi-scale quantum algorithm, then again, the cost is independent of epsilon. If you do a brute force explicit method, I mean, still have a dependence on epsilon. Although it's a little mild, but still it depends on 1 over epsilon. So it looks like that even at quantum level, quantum computer level, I mean, the multi-scale methods still help. All right, now what we are mainly interested in is nonlinear ODE and PDEs. All right, so these are some examples in general form. Here, not only we want to solve do one simulation. Actually, we want to simulate the same equations, but with many initial data. For example, if you want to do uncertainty quantification, if you use Monte Carlo method or other sampling method, you have to run multiple initial data and then take on sample average, right? So you have to solve one equations, but multiple times for both ODE and PD. So here we assume that you have initial data, capital M different initial data. So this superscript K represent all this M version of the computation you're going to carry out. But the first challenge is whether a quantum computer can do nonlinear problem at all. All right. Of course, I mean, I don't have to convince you that the nonlinear problems are important. I mean, all over the place, from fluid dynamics, molecular dynamics, and so on, mathematical machine learning. There are also other challenges. For example, you may have singularities and then a curse of dimensionalities. And very often you have to do a lot of simulations. For example, in Monte Carlo, I mean, you have to do a lot of simulations. So there are a lot of numerical parameters here. I mean, d, little d and capital D are the dimension of a PD and ODE. Epsilon is the error. Capital T is the output time. M is the number of initial data you want to run your simulation. For example, the number of samples in the Monte Carlo simulation. And so we are basically, we are not able to have a quantum algorithm for general PDEs, but we do have good algorithm for Hamming-Jacobi equations and hyperbolic equations, nonlinear hyperbolic equations, scalar one. Okay. So those are examples I'm going to present. So the first question is, are nonlinear problems suitable for quantum computing? After all, the quantum computer is built on the principle of quantum mechanics, and we all know quantum mechanics, like embodied Schrodinger equation, is linear, all right? So people have a time to see whether we have so-called nonlinear quantum mechanics that can be solved by quantum computer. So this is a paper published by Seth Lloyd. Well, remember this HHL algorithm, this L is actually Seth Lloyd. He's a professor at MIT. So in 1998, he published a paper in Physical Review Letters where he did some simulations for nonlinear problem, and this is his conclusion, all right? So he said in the end of the paper, we would like to note that we believe that quantum mechanics is in all likelihood exactly linear, and that the above conclusions might be viewed most profitably as further evidence that this is indeed the case. So basically, he wrote this PRL paper, and he ended up with the conclusion that indeed quantum computer is linear. All right. So now then, how to solve a nonlinear problem, nonlinear PD in particular? There are only two choices. All right. First, you make the problem linear. Or second, you abandon the fundamental quantum computer principle. I mean, you design quantum computer based on a different physics, all right, not based on the physics of quantum mechanics. Well, of course, nobody knows how to do two, so let's stick to one. And there are some works which I cited here at the end of the slides. There are some works which try to solve a nonlinear PDEs and ODEs based on so-called linearization. So that's the most natural way, right? You have a nonlinear problem, you don't know how to solve a nonlinear problem, you first linearize, okay? Linearize. So we call these methods linear approximations. So one of the preferred methods is called Kalman representation, which works quite well. It works for usually quadratic equations. So you have, for example, du dt u equals u square, and you let u square to be v. Then you derive equation of v, and then you never stop. You have infinite hierarchies. All right, you can never have a closed equation. Then what you do is like what people typically do in a kinetic theory. You truncate. You throw away high order moments. So that's what the state-of-the-art methods for solving nonlinear PDEs. Of course, if you do this kind of approximation, you encounter problems. For example, they usually work well for weak or special in nonlinearity, like quadratic or nonlinearity. And if you truncate, then there's no guarantee that this model will be valid for a long time, especially if you have a strong nonlinearity. Okay. Well, what we advocate is so-called not a linear approximation, but linear representation. Okay. By that we means that we try to find the exact map which maps the nonlinear problem to a linear problem. Okay. Well, in this direction, there was some work for ODEs, for nonlinear ODEs, using the so-called Kupperman-von Neumann approach. Okay, by this group of people. Most of them are actually plasma physics. But so far, before our work, there has been no work for nonlinear PD. So that's what we're gonna do. So I'm going to use the Hamming-Jacobi equation as an example. So here's the Hamming-Jacobi equation. So S is usually phase, H is Hamiltonian. All right, it's a nonlinear operator which depends on the gradient of S and also the X variable. Here X is a D-dimensional vector. Okay. So we solve initial data. We're going to solve capital M initial data. So can solve this Jacobi equation m times. If you do classical computation, you have to solve m times to take ensemble average. So our approach actually is based on earlier work of me with Stan Osher, where we use level set function. We use level set method to solve a Jacobi equation. The way to do it, first you take gradient of s. Okay, we call that u, where if s is phase, u is velocity. Okay, u is the d-dimensional vector. Now I define the level set function phi by introduce. So phi is defined in the phase space. All right, s is depend on t and x, but phi depends on t, x, and p. And you want phi to be 0 when p equals u. Okay. So the 0 level set of phi give you u, the solution u. Well, that is a very simple calculus to derive equation for phi, which actually is exactly this Liouville equation, this classical Liouville equation. And with the Liouville equation with Hamiltonian, that's h. Now this h actually depends on, because now the gradient s is u, which is p. So this h will depend only on x and p. Does not depend on phi. So therefore, this Liouville equation actually is linear. All right. And for initial data, it's very simple. You just take the initial value of phi to be simply p minus initial data of u. Clearly, phi is 0 when p equals u. Okay. So you just solve this Liouville equation with this initial data. Then you just plot the 0 level curve phi. That give you u. Okay. But however, I mean, finding the 0 phi is impossible for a quantum computer. For classical computer, this is trivial. If you use MATLAB, you just find the contour, right? In 2D, 3D is isosphere. But quantum computer does not how to find the 0 of such a complicated nonlinear function. Okay. So to avoid finding zeros, what we do is instead of solving for this phi, we introduce another function psi, which basically is the delta function of phi. Okay, it's delta function of phi. And that also superimpose all the different initial data. Remember, we have this m different initial data. Now we just superimpose all the m initial data, all right? And then by the linearity, actually can prove this psi also solve exactly the same Liouville equation. But now with the initial data, which is a superposition of the initial data of delta phi. Okay. Now, if you solve psi, you do not have to solve the m times to get the physical observables, get the ensemble average. You just have to solve the equation once. Okay, you only have to solve the equation once, despite we start with m different initial data. Now the question is, what is the connection between the psi and the u, the solution of Jacobi equation? It turns out that if you take the moments of psi, all right, for example, this g of p, if you take g to be 1p or p squared over 2 actually, then you will get so-called this moment, the moments of psi actually give you so-called position density, momentum energy, which are corresponding exactly to so-called semi-classical limit of Schrodinger equation. If h is the classical mechanics, if h is Hamiltonian for classical mechanics. So these physical observables are nothing but the physical observables, I mean, about the physical observables Schrodinger equation by passing this h bar to 0. So you can exactly get those. So those are exactly physical observables, all right? So these moments of psi give you physical observables. Now we do not have to find a 0 level curve because you just have to take integrals, you approximate the integral by Cauchy rule, okay? I have to make a remark. Well, for those who are familiar with Jacobi equation, we know the solution of Jacobi equation actually has singularity called caustics. Okay, so when you have caustics, beyond caustics, then you have to define sort of the weak solution. So there are different notions of a weak solution. The most important one, of course, is called a viscous solution, introduced by Crandall and Lyons. But here, this level sub function will not give you the viscous solution. Instead, it gives you so-called a multi-value solution. And this multi-value solution actually is exactly the solution, the correct solution, which arises in the semi-classical limit of Schrodinger, or the geometric optics limit of high-frequency waves. All right. So difference between viscous solution, for example, if you have Burke's equation, well, sorry, cannot see this. They start with the sine function, eventually get this shock waves if you solve Burke's equation, all right? While the multivariate solution actually, instead of shock, if you solve by method characteristic, you get this multivariate solution. But shock solution, you draw a line by using equal area rule, you get this shock solution. And we also know, this level set method or Hamming-Jacobi equation arise in simulation of front propagation. So imagine you have two circles that expand in normal outer normal direction by constant speed. Sooner or later, these two circles will meet for cause the singularity. So beyond singularity, if it's a level, if it's a viscous solution, is the graph on the right. If it's a multivariate solution, then you have this superposition area, where the density and the velocity have a satisfied linear superposition. So this multivariate solution are exact solution the level set method give you, which is sort of the semi-class limit or high frequency or geometrical limit of high frequency waves. Okay, so those are the solutions we compute. We're not computing viscous solutions. And same level set, this level set method also works for scalar nonlinear hyperbolic equations, but not for general hyperbolic PDEs. For example, it does not work for a system of nonlinear hyperbolic equations, only for scalar ones. Okay, so now we have a linear PDEs, right? So now we're going to utilize this quantum linear algebra solver for this linear PDE. And the way to do it, well, now we take a classical finite difference method, for example, with upwind method, all right? And then we put into a linear algebra form. The way this quantum linear algebra solver works is that now this psi, well, in classical computer, you do time marching, all right? You march forward in time. But here, actually, we put this all time step into one big vector, this phi. But the second index j, this index corresponding to the meshes. But the first index is corresponding to time steps. So phi 1, 2, and all the way to nt, where nt is the number of time steps. So put that into big column vectors. And then this finite difference method can be written in by this linear algebra with this big kappa matrix, all right? Which has dimension of the number of mesh points times the number of time steps. It's a big matrix. The right-hand side are just the solution vectors, the initial data, all right? But the quantum computer, usually the quantum gates are unitary vectors. So this k is nothing unitary. So what we do is first we have to make it commission, all right? So we use this dilation to make this k this M matrix, which is a commission matrix. And then you put in the quantum computer, then we know e to the I m t is a unit vector. So once M is a unit vector, this quantum algorithm, the quantum gates, basically was evolve e to the ITM. Okay, this matrix, which is unitary matrix. All right, now we solve this linear algebra problem. It's called quantum linear algebra system. And suppose this matrix is 2 to the power m by 2 to the power m. Okay, now this little m is basically the number of qubits you use. The classical solver for this linear algebra problem typically costs 2 to the power m cubed. But quantum algorithm costs, you take this log factor, all right? So you get exponential speed up. However, I mean, the classical output give you x, which is m inverse y, while quantum computer, you have to evolve quantum states. So essentially what you output, you basically solve m, the x cat equals y cat. Therefore, the x cat is basically m inverse y cat. So you're going to get this x cat, all right? This is the quantum state of x through so-called oracles, all right? Of course, you're not going to solve this exactly, so you assume that you're going, instead of getting x hat, you get x prime hat with the error, which is eta. So you have you allow this error, which is eta. And the cost of quantum computer is basically how many times you query these oracles. Okay, so you access this matrix through oracles. Actually, I mean, well, for classical computer to input the matrix is trivial, but input the matrix in the quantum computer actually is highly non-trivial. It can be very expensive. Okay, and so, well, of course, once you output this x cat, you still have to do measurement, which is very expensive. So instead, we do not solve it that way. Instead, we use this so-called SLEP process. We solve so-called system linear equations. So if you start with mx equals y, what we want output is this expected value x transpose of this g, which is like moment. The vector corresponds to moment. I mean the matrix operator corresponds to moment, and x. Of course, the quantum state version of x transpose gx. Okay. And so that's the kind of output we're going to provide. And of course, here you have to first you have access to the matrix M. You also have to access this moment operator G. So the cost is based on how many times these oracles are queried. Okay. Well, usually to encode a full matrix into quantum computer is very expensive. And it becomes efficiency if you assume that this M is sparse, which of course, if you solve a PDE, of course, M is sparse, right? If you use find difference method, actually. Okay. So these are the oracles which input this M. So this OM is the oracle that input M. OF is, I mean, you have to remember the non-zero entries of this M. So this OF basically remembers the column and the row indices of these non-zero entries of M. So you need these two oracles, OM and OF. All right. Okay, so we're going to output the moments of psi, all right, this G with this G. So you have to start with a quantum state of your initial data, psi 0. And we approximate these moments by this quadrature rule. Okay, quadrature rule, which is sort of inner product between this G vector and this psi vector. All right, so you have to first you have to input your initial data psi 0. You also have to input this G, which is the moment, these moments. All right, and what we do is basically you evolve. You start with psi 0, evolve by M inverse. All right, then you do this the moments, which are basically this self-adjoint. I mean G. We make G to be a symmetrical operator. All right, so you output this epsilon. Then the moments are but nothing but basically square root of epsilon. Those moments we're going to output are square root of this epsilon. So we're going to design quantum algorithm to output this epsilon. And here are some details of a quantum algorithm. Basically, you need some. You have to assume a sparse access to M. Well, M is sparse matrix. All right, so we do have a lot of sparse access. And also you have to input your initial data into quantum states. Then you have this, these are standard oracles to access your matrix. We assume that you have access to M. You also have access to M inverse, same for G and G prime. G prime is the transpose of G, all right? Then you, through this so-called amplitude estimation, that will give you epsilon with the error, which is epsilon prime. So that's essentially the quantum algorithm, the entire quantum algorithm. It's based on the original work by Sanders, the way we implement this. So these are actually the cost, computation cost, which depends on D is the space dimension, capital T is the output time, epsilon is the precision. Of course, there are a lot of powers here, but I want to compute with classical algorithm, which is given here, all right? The M is the number of initial data, so you have to solve the same equation but M times. That's why you have this cost that's linear in M. So we're going to basically divide the cost of a classical algorithm over the quantum algorithm, all right? And the right-hand side basically have D R to the power R1 and 1 of epsilon to the power R2. And you want R1 and R2 to be positive to have quantum advantage, because when R1 and R2 are large, bigger, are positive, then this cost of C over Q is large. Okay, so here we have a table for different equations and what condition to make this R1, R2 positive. For example, for D plus 1 dimensional Hammond-Jacobi equation, so his dimension, X is dimension D plus time 1. So therefore you can see as long as if the dimension is sufficiently high, so B actually has to do with the support of initial data. So for sufficient high dimensional problem, we do have quantum advantage in both the dimension and also this error. All right. So you have quantum averaging for both D and or epsilon, as long as sufficient D is enough. And you always have quantum advantaging this M, because we only have to solve M different in unitary only once to get this ensemble average. But the classical cost always depend on linear in M. So we do have quantum advantage for high dimensional problem, also for epsilon, for both D-dimensional Jacobi equation and also D-dimensional scalar hyperbolic equations. But for ODEs, you see that R1, R2 are always negative, which means you never have quantum advantage in D and epsilon. And you only have quantum advantage in M. And for general nonlinear PDE, for example, Navier-Stokes equation, all right? Well, there are two ways to do it. One is Lagrange method, for example, you use vortex method, which are based on particle method. And or you can also find a difference method to solve for X first, all right, then becomes ODE, then you use this ODE solver. As you can see, you never get any quantum advantage for both the dimension and the epsilon, but you do have a quantum advantage for M, for the number of initial data. All right, so to conclude this part, I just give a very summary. First, we know the physical world at the microscopic level is fundamentally linear, at least in the quantum level, and also at classical mechanics level. Of course, Newton equation is nonlinear, but Liouville equation is linear, all right? It turns out these macroscopic models are often nonlinear. The reason they become nonlinear is because if you start with linear equations, you take this mean field limit by assuming molecular chaos. It becomes nonlinear, moment closures and so on. So for classical computer, we want to do dimension reduction. Dimension reduction is very important for classical computer because you cannot afford cursive dimensionality. But for quantum computer, actually, we did the opposite. We increase the dimension, all right? But we make a nonlinear problem linear. So we take different directions. So that's very different. So the conclusion of quantum computing is not very sensitive to cursive dimensionality, okay? But you want the linearity. Of course, I mean, this cursive dimension cannot be too much. For example, for Hamming-Jacobi equation, a scalar nonlinear hyperbolic equation, I mean, we only double the dimension. That's not a problem. For classical problem, double the dimension kills you, all right? From Shorty and from Navier-Stokes to Boltzmann, I mean, that's too much. But for quantum computer, that's not a problem. However, if you find difference for Navier-Stokes equation, then you make a D-dimensional problem to n to the power D. Well, that's too much. That's really too much. Okay. All right. So how much time do I still have, Robert?
I think you're up. Your time is up. Actually, if you could,
so I finish in 5 minutes, very quick.
Okay.
So finally, because this is a UQ meeting, so let me tell you very quickly. All right. So I use a very simple example. This ODE with this A of U, which contains uncertain parameters. So Z is some random variables. Okay. So of course, if you do Monte Carlo, you have to take a lot of samples, you solve this equation and take average. Okay. So what we are interested in is the case you have to solve a large number of samples, initial data, get ensemble average. For example, in Monte Carlo. So actually, this idea is based on a previous work by Francois Gauss. Well, of course, they were doing homogenization. It has nothing to do with what I'm talking about. It's a different problem. But the same transformation, it works beautifully. So what we do is we introduce another variable W. So we start with little u, which depends on T and Z, with these high dimensional random variable. You let the capital U, which depends on T, Z, and W, which equals A of Z times e to the minus W A of Z times U. And W has to be positive, non-negative parameter. Then you can write the equation for capital U, which actually is a linear wave equation, all right, with this initial data. Now you can see the equation, the coefficient, there's no more Z dependent in the coefficient, okay? Of course, you can recover little u by integrate capital U over W, take these moments. So now the only place where Z appears is the initial data. So if you want to solve, for example, if you do Monte Carlo simulation with many samples, ZM, capital M samples, you just linear superimpose the initial data and then you solve one equation. All right, you get the ensemble average. So therefore, now the cost is independent of M. Of course, this works even for classical computers. All right. However, in classical computer, if I say I want to increase dimension, people will kill me because they want to reduce dimension, not increase dimension. But after hearing my earlier talk, now you realize adding dimension is not a problem for you. But now I can solve this higher dimension problem in a quantum computer. A similar idea works for other equations. For example, linear heat equation, if you have the heat conductivity is uncertain, you do the same transformation, then you get these third order equations, all right? Or I mean, you still have the Laplacian, but you get this EDW term. And also for linear transport equation, I mean, that's the topic of this workshop. So for example, if scattering coefficient is uncertain, okay, then the same transformation will get rid of this sigma z from the equation, and they only have this z-dependent initial data. However, if you have a linear equation, you have a linear wave equation, and you do the same transformation, then it's not good, actually. I mean, you get this, if you do the same transform of a linear wave equation with a speed of wave, which depends on z, you get this equation which is a linear opposed. And what you need to do is you take another transformation with square root of a of z here. Then you get a third order derivative, okay, in this term. You get rid of this a of z, but you have third order derivative. And you can prove this equation actually is well opposed. All right, the second order derivative with partial x and w, that's E opposed. But the third order derivative with second derivative in w is well opposed. Same for Schrodinger equation. So suppose you have uncertainty in the potential in the Schrodinger equation, all right? And now you have, it's the same as wave equation. You have to introduce this square root of a of z here. So then you get a new equation for capital U with a second order derivative in w. But the second order doesn't matter because you already have second order derivative in the Laplacian U. And so what is quantum advantage? So here again, I use same notation. So they can see actually you do not gain much quantum advantage for the dimension, but you do have advantage in the epsilon if dimension is sufficiently high for all these equations. And you always have quantum advantage for m. You only have to solve, if you do Monte Carlo, you have to do it just once with m different samples. Well, they say, well, this coefficient is very simple. How about the more general coefficient? So if I'm a general function of a of z, which I don't know how to do, but if it's linear superposition of a of z, function of z times function of x, then we can do it. But of course, this is not very special because if you do, if you use Calvin loop expansion or polynomial Kells expansion, you always have these answers for this uncertainty coefficient. There, of course, you have the L dimension of W. Now you need the L dimension. So if you have L terms here, the W has to be dimension L vectors. So that means you're going to end up the equation, which is Laplacian with the U now has dimension L dimension. Okay, you increase dimension by L. But that's not a problem for quantum computer, all right? This L is a fixed finite number, so you can deal with this quantum computer. And well, the nonlinear, well, then it's tricky because first you discrete in space, make it to be ODE, or then you can use this level set approach to make it linear, okay? And we can gain advantage on M for all nonlinear PDEs, but not necessary for the other parameters, not necessary for dimension and for epsilon. Okay, so finally, this last slides. So first, we know, I mean, our quantum, this is the first quantum nonlinear PDE solver based on linear representation. We're not changing the model. We use exactly equivalent models. There's no linear approximation at all. We gain quantum advantage for this number of initial data, dimension, and also the error, okay? And our quantum advantage are gained even by including the measurement step. Before our work, when people talk about quantum advantage, they only compare quantum subroutines. This first time we get quantum advantage by including the measurement step, which are the physical observables. And well, for PDEs with uncertain quantifications, I mean, if you use this phase-space approach, we gain advantage on M. Okay. But of course, this is just the beginning. There are lots of interesting questions ahead. For example, how to do linear general nonlinear PDEs, how to get viscous solutions, how to do high dimensional dynamic system, for example, molecular dynamics. So there are lots of open questions. I think it's beginning. I think it's important and very exciting field, but it's really, I mean, it's completely open. So there are lots of questions that remain to be answered. So with that, I stop. Sorry for the delayed
Thank you.
delayed